Howdy folks, on the bench today we have this control board out of a Viking oven. I will put the oven model number here if I can find it. And this is not the first control board for that oven that has failed. And rather than buying a new one, which is becoming harder and more expensive, we're simply going to repair one of the old ones. I say one of because this is the first control board that came with the oven. It's dated 2006, which is roughly when the oven was installed. And there's another replacement board in there now, and it has just also failed, so which I don't have, unfortunately. So I'm simply going to repair this one and put it back in. And I want to go through my process for doing the repair, as well as the part selection. We're going to be doing a bit of an upgrade on this to try and make sure that it doesn't fail again, at least in certain ways, because we're not making thousands of these. We can spend a little bit more money and sort of upgrade some of the parts to try and make it a little bit more robust. This oven is very large, very heavy, very difficult to get to the control board. It's also a built-in. It matches a bunch of other appliances, so it's not really practical to get a new appliance. And honestly, a new appliance would probably be far more unreliable anyway. So it just makes a lot of sense to spend the money and fix this once, because even getting a repair tech to get to the board is very, very difficult. It's not my oven, it's somebody else's, but I'm doing this support for them. So this particular board, there's the model number 841130C. So it's relatively old, and that's kind of nice because the only software on this is this little ATmega. I think it's a 16L. ATmega 16L8 on here. There it is. That's basically the only part on here that is something that we couldn't replace, honestly, because of the firmware on there. Everything else is honestly off the shelf, which is really nice. This is a very, very repairable board, and I think that's why we're going to be doing this. So as for why it doesn't work, well, this terminal's bent. I think that was something in storage because I've had this board for quite a while. This relay has an X on it because it is dead. If I shake the board, you can actually hear something's rattling around in there. So there's a serious mechanical failure. And if you're wondering why it failed, well, when you flip it over, it has a little bit of an oopsie has occurred here, where the trace has completely vaporized near the pin there. So that kind of explains as to why it doesn't work. And so that is on this relay, which is for the bake element, which is the most commonly used element. So there's no surprise there. The other board, the one that has recently failed and what this one's going to be replacing, what ended up dying on that one is this relay here, which is the double line break. This is for safety. This cuts the other side of the line. I think the contacts wore out in that relay, and it went high resistance, and it got so hot that it melted the relay and the cable connected to it and everything. So that's the fault on the more modern board, which I'll probably be, I'll be putting that board in inventory once I swap it out with the fixed version of this one, because again, it's good to have parts for these things. And of course, this relay is just dead, probably due to whatever kind of overcurrent condition caused this, because obviously this is a high current that caused this. It's possible that there was a crack in the solder joint, but usually it wouldn't result in something like this. And of course, it not only blew out on this side, but it also would have blown out on the other side underneath this relay, which we'll take a look at once I get this off. What I suspect happened here was probably one of the other faults on this oven. So it's gone through two control boards. It's also blown at least two of the elements have catastrophically failed. One of them I think was an independent event, and I think one of them died at the same time as this board. It's testing my memory, but I think what happened, I think it was one of the elements that blew that took this out. And an heating element is just a long resistor, and so when it fails, it'll usually fail open or higher resistance, right? It can go to any arbitrary resistance all the way up to an open circuit, and that wouldn't result in an overcurrent. So what I think happened was the actual element, I think it actually blew in half, and one side of the element actually drooped down and touched the metal chassis of the oven, which is connected to ground. And so you had this shorter section of, I don't remember where the break was, but you had a shorter section of heating element between line and ground, and that went through this relay, and I think that's where the high current came up that blew that out and obviously destroyed whatever's inside. So I'd like to open this relay up. When we're done, we'll get the Dremel out because I think it's sealed, and we'll see what's inside there. Now, when it comes to refurbishing this board, I want to make a few changes and upgrades before we put this in, because again, a little bit of cost now saves some headache in the future. And of course, we're going to have to replace some relays. So just so that we'll go over the board just so you know what's on here. We've got 4 high power relays. These are 30 amp rated relays, and these are for all of the 4 main heating elements. These are all 240 volt heating elements. So one side of the line goes, through this relay, and then there's a common that goes to the other side of the line, which goes through this, which is a line break relay. This is for safety. It takes off the other side of the line. We've got these smaller relays, which I think they're 10 amp, and these are just for like the fan, the door lock, ancillary functions that are lower current. We've just got a regular linear power supply, so the line comes in here, goes through this. We've got a bridge rectifier, and then we've got a 12 volt output. Looks like there's a zener there, so we have a 12 volt output, which is what drives all the coils. All the coils for all the relays are 12 volts. We then have, I think this is, being used as a pass transistor. Don't quote me on that though. We have a lower voltage, I think it's a 5 volt rail, which is what runs the logic. We've got our AT Mega, we've got a little resonator for that. And then it's got some 7.4 series logic, which then goes through a Darlington transistor array, which is what drives the coils of all the relays. And then we just have a bunch of connectors for all of the control panel and stuff and all those other things. And there's some LEDs they've put with all the coils. Every relay has an LED, so you can actually see when they're on, which I guess makes sense for the techs working on this. And there's absolutely nothing on the back side of the board. It's all single-sided. And this zip tie is factory. That's just the way that they affix the transistors, or the transformer, so it is what it is. So in terms of replacement, obviously we need to get a new one of these, and I'm also going to be doing a bit of an upgrade. So I am going to be swapping them with better quality relays. If you have a control board and you have a relay failure, obviously you can just look up the part number and get a data sheet for it. Usually it'll be a data sheet for the whole series, and then you have to decode what the part number is to get the exact specs of it. And then you can find something that is equivalent to that or buy the exact relay. Generally, buying the exact relay is not the easiest thing to do. Usually, a lot of things like this, they have sort of a Chinese brand, and therefore you'd have to get somebody to import it for you. The major distributors aren't going to carry it. It may be discontinued depending on how old the product is. So it makes more sense to just get a compatible replacement. Usually you can save some money, and you can also put your money in and get a better part. And so that's exactly what I've done here. This is from, I believe, a CIT relay. And this is a 50 amp relay. So this is a 30 amp. This is a 50 amp. So it's the exact same form factor, exact same pinout on the bottom. It's a sealed relay. There are a bunch of standard relay footprints. So you can get a set of calipers out and take some measurements between the pins and the housing, and find one that's exactly the right kind. So the newer relays are upgraded, and I'm doing that mostly just for reliability. Obviously, we know that it can't exceed 30 amps, and this one being rated for 50 just means it's going to have more robust contacts. This one, for example, the internal contact resistance initially is 50 milliohms. This one is 30, so we have lower contact resistance. And I think this one, the electrical life is 20,000 cycles at, I think, 66%. Rated current, whereas this one's 100,000 cycles at 100% rated current. So significantly longer electrical life, and that's what we want. We don't want the relays to be the failure point. Just like in the one that failed, this relay was the failure mode. So we'd like to try and, just make sure that whatever we put in doesn't fail for the life of the appliance. So we don't have to do this again. So I got some of these relays. I've also got, I just went with CIT relay for everything. I've got a replacement here, and this one is a 40 amp, job, and it's going to go right here. So other than the fact that the terminals are in a slightly different orientation, but there's just cables that go to these, so it doesn't really matter. So that's the replacement for this, and again, it's upgraded there. And then I've also done the same thing for the small signal relays. I've also gone with slightly higher reliability. They're not higher current, but they do have better specs. And so these ones are just the same as for all of those. So those are the relays. I think those are pretty straightforward things to be replacing. I'm also going to replace the 3 electrolytics as a matter of course. These ones are working just fine, but they're from a brand that I have never heard of, HEL. Well, I mean, yeah, who knows what these are? They're also 20 years old, and so it would be really dumb to not spend the $3 and just replace these. Now, the reason they're probably doing so well is because this is a linear supply, so there's very little high frequency ripple and stuff, so that tends to make them last longer. But for $3, I can buy a set of like basically the best spec capacitors. So I went with a high-end Panasonics for all three caps, and they're all rated at greater than 5,000 hours at 105 degrees C. So basically, caps that will last the lifetime of the unit. So that's, I think that makes a lot of sense to do as well. And then the only other chip that I'm going to be changing on here, the only other component I'm going to be changing is this chip here. This is the ELAN 2803A. This is like I said, it's a Darlington NPN transistor array, and that's what they're using to couple the logic from the microcontroller. They're going through the 7.4 series logic into this, and that's what drives the coils. The reason I'm replacing this is because I don't know whatever event happened here. It's possible that it could have damaged this transistor. If there was arcing in here that went to the coil or whatever. I don't know what the state of this chip is, and it's not worth my time to test it. So for the $3 the chip costs, I just bought another one. It also means that I know the brand. I don't know the brand logo of this one off my head. It's probably an Asian brand. So I'll get one that I have a data sheet for, and I know that it will be, I know what its ratings are, and that's important because the coils on the new relays are not the same as the coils on the old relays. So the coil current for the new relays is slightly higher than the old one, and so I need to make sure that this can handle that current, and it can. It's still several times overrated for the coil current, but it's an important thing to just check if you're ever doing a replacement like this. We have a big enough power supply to drive all the coils at the same time. No big deal. This stuff takes almost no power. But if you had a more conservative or more restricted design when it came to things like that, you may want to spend more effort trying to find the exact relay that specs that you want. So I think at the end it's got this 1.5. I think that's the coil power, 1.5 watts. And you can also get it in, I think 0.9 or whatever. I ordered these a bit of time ago, so I don't remember exactly, but all I know is it's slightly higher than this, so it would be something that you'd want to check. And I know you can get lower powered coils in this series, but they were not as readily available, and it didn't really matter for what I was doing with. Anyway, so that's what I'm going to replace, just going through all of this. And then as far as the board goes, what I'm going to be doing for this is I'm going to drill a hole just with my drill press through here that's larger than this area, and we'll get all of the we'll just get it. It's really this failure is actually normally when you blow traces, it's not really conducive to easy repair, but this is actually a very easy repair because there's no other traces around here. We've got this massive gap around everything, and so this was the only this trace is the only thing here on both sides of the board. So what I'm going to do is I'm going to drill it out. I'm not really drilling it out to get rid of the carbonization here because it doesn't really matter that the board's conductive here. I'm drilling it out, A, to make it look pretty, and B, because what I'm going to do is I'm going to basically just use a low gauge wire to connect this terminal to this terminal, and I want to just basically wrap the wire completely around the terminal to get a really nice connection to it, and I'm going to just sink that into where the board would be, so it looks really nice, and I just need enough clearance around the pin to be able to get that wire in there. So that's what I'll just drill that out, and we don't need to worry about the top side because that wire is going to have more than enough current carrying capability on the bottom side to this spade terminal lug than the track ever had. So no big deal there. And they're not using these traces as fuses, so it's not like I'm the fact that it blew out here is just happenstance. Like you look at these, they're not using these as fuses, so I'm not removing any kind of safety protection or whatever on the design. So anyway, let me get my desoldering iron out. I got to take all 10 relays off, the caps off, that chip off. I'll do with hot air, and I will bring you back, and we'll take a look at what it looks like under this, and then we'll start repopulating the board. I've just finished depopulating all of the relays and other components that I'm going to take off the board. Looks pretty barren now. You can get a look at what the other side of that blowout was. It's not as bad as the other side. I haven't cleaned the soot off this one like I did on the back side, but you can see the trace is gone here. The trace might actually be intact here. It's probably just the through-hole plating that failed because that's the smallest cross-sectional area. But anyway, it doesn't really matter. I'm going to use some desoldering braid to clean up the holes, and then I got to put this in the drill press to just get rid of that area and give myself some space so that I can attach a wire to that terminal. The desoldering iron took care of the relays. They were actually not as bad as I thought, and I got the coils with that as well, and I just had to manually do the big lugs because I wasn't going to wait for it to cool down to change tips. But yeah, this is going pretty well. I will bring you back when I've drilled that out and repopulated all of the relays, and we can see what it looks like all fresh and ready to go. Before we do that though, I'm sure you would like to see what's inside the relay that failed. So this is the what's left of the pin. It's actually surprisingly intact. It's just slightly charred. This is a sealed relay, so I'm going to see if I can brute force my way into this, and we'll take a look at what the contacts look like. Here's the inside of that relay, and I just squished it in a vise and broke the seal around the outside. The casing of these relays is so incredibly thin that it just shatters. So it was easy to get it apart without too much damage. Now, I was wrong about the rattling thing. The rattling was not actually this relay. It was actually the small relays next to it. These things naturally rattle, but because they were right next to this one, that's why I thought it was this one. So it didn't have a catastrophic mechanical failure inside, but the contacts definitely do not look good, though. I'm going to see if I'm going to get them apart, but you can see the bottom side of that contact there. Which is the normally open. That's the one that's being used. The normally closed is not even actually connected on this one. It's not a real contact. It's pretty black. It's definitely seen better days. So let me just rip this thing apart, and we'll take one last look at it. These are the contacts out of that relay, and as you can see, they are not looking so good. There's lots of scorch marks from the arc flash, lots of soot on both of them. You can actually see through the plating, it's gone. You can see copper through on this one, and this is the stationary contact, and it's all pitted, and this relay was done. This thing, if the track hadn't blown out and the thing was continued to be used, this would have just probably melted due to internal heating from the poor contact resistance. What I think I might do is I might open up the line break relay, because it's got the same number of actuation cycles as this one does, and I'm curious to see the state of its contacts, just without the the event that occurred, just to see kind of an A/B comparison as to what the contacts look like. Because from the same company, I'm sure they'd be basically identical in terms of their manufacturer. So let me see if I can crack that relay open easily, and we'll take a look at that before we get back to everything. So I got the contacts out of the other relay. I just squeezed it in a vise like I did the other one. It didn't want to open nearly as easily. I think it was more structurally sound, being a proper rectangle, but I got the contacts out, and as you can see, they are pretty good. There's a little bit of discoloration. You can definitely see the point of contact, but honestly, these are not that bad. Given their age and the number of cycles, these look perfectly fine. They're wearing, but these would work just fine. And the one thing I don't know is exactly how the firmware handles the sequencing of the relays. I don't know if this relay is, if it makes this connection first, then it makes this connection, and then does it break this connection and then break this connection? Because if it did that, this relay would never actually see making or breaking of any current. It would always be on the other relay. So that's possibly a reason why this one was fine. Or maybe it just fires both relays at the same time, and then just whichever one mechanically moves first is the one that does it. That actually sees the one that moves slower is the one that actually sees the current. I don't know. I would be really interesting to see if it's sequenced. It makes a bunch of clicking noises when you turn it on. So to me, it sounds like it's engaging this first, then this. So this one takes the brunt of everything. But I don't know. You know what? I'll make a follow-up video when I get my hands on the other one where the line break relay failed. And I'd really like to see what the deal is there, because that might invalidate that theory, or it's possible the firmware is different because it's a newer board. Who knows? Well, anyway, that'll be for a future video. But anyway, I just wanted to show you what the comparison is. And yeah, it's a pretty stark difference. So let me get to drilling out and prettying up that board to receive new parts. Just finished cleaning up the board with some solder wick. All the holes are nice and clear, and I've used a 1/4-inch twist drill to just take a little bit out of that hole there, and use some side cutters just to cut the trace nice and flush with the hole. And so now it's time to repopulate everything. I quickly realized that I had made an error in speccing these relays. Now, because these are 50 amp, their pins are pretty big. And I measured the diameter of these holes, and it was, it would have worked with the size of these pins. However, these pins are actually, they're actually square rather than round, so you actually need, of course, a bigger round hole to fit this in. So these actually do not go in the holes all the way. So I have two options. I can either drill out these holes, which is easy, but then I lose the through plating and I have to rely on the pin to actually wick the solder from the backside to the front side, because we do need this other layer to conduct current. So that's a little bit risky there. The other option, which is not as fun, is to just use like a flat file like this, and to essentially just shave the pins down and make them round so that they fit in the holes. And I've just, whenever I order parts, I usually order N+1 just in case I screw one up, or if one's defective or whatever. And even if I don't use it, I get to put it in my stash and then I have something for later. So I just did this on my N+1 relay, and it now fits nicely. So I think I only need to do it for the 4 relays here. All the rest of them, all the components will fit fine if it's just these ones. So I think, given it's only 8 pins, I think for the integrity of the board, I'm just going to do what I did here and just shave them down. So a little bit of a minor inconvenience, but not something we can't handle. And of course, these pins are overrated as it is, so it's not like I'm removing, removing material that needs to be there. So just slows me down a bit. A little bit of time later, all of the relays are installed. I've put the caps in as well as the transistor array. I've put a lab power supply across all the relays. I did that before I put the transistor array in, and they all work, so that's good. And the last thing to do is to deal with this whole blowout situation. And so for that, I have made, out of some solid core wire, little tiny jumper here, and it just kind of sits around the pin like that. When you get it all nice and situated, it just wraps around the pin, gives a nice area for solder. And this is thicker than the pin is, so we have more than enough current carrying capability right to the lug. And then it's so short I don't have to do any kind of gluing in the middle or anything like that. And then once that's in, I just have to clean all the flux residue off just to make the board look nice. This is no clean flux, but I might as well. And then we're ready to reinstall it. There we are, all soldered in. And so I'm not going to take you through the cleaning process. That's pretty straightforward. And so yeah, this is not really much more testing I can do. I got to hand it back to the owner for that. And yeah, hopefully you've learned something, or maybe you've got one of these or something similar, and this has given you insight and maybe a little bit of motivation to try and doing some board repair for yourself for some of these simpler appliances. More modern stuff, they've got way more electronics, way more microcontrollers. When it comes down to where the rubber meets the road with the controlling of power and simple things, heating elements are just they're just resistors, they're just switches. So if you have these kinds of failures, I highly encourage fixes like this. And so hopefully this thing lasts a lot longer than the last replacement board, but only time will tell. So till the next video, thanks for watching.